All right, these are the video solutions for real batteries aren't perfect, and neither is this video going to be, but maybe it will. Okay, let's see what we got here. Question 1. You have a battery with an, I'm going to say, ideal voltage of 70 volts, an internal resistance of 3 ohms, is hooked up to a 150 ohm stereo speaker. Calculate the current in the circuit. So Ohm's law says I equals V over R. The voltage is 70, but you lose some energy inside the battery and then you lose some energy outside the battery for a total of 153 ohms. And that gives a current of about almost half an amp. And there's only one current because there's only one loop. All right, calculate the terminal voltage of the battery. So the terminal voltage from terminal to terminal is your ideal voltage minus I little r. We thought we were going to get 70 volts, but we got a little bit less than that because of the energy lost inside the battery, and that gives us 68.6 volts. Okay, so this 150 ohm, if you hook this up to a perfect 70 volt battery, it would be brighter, right? Because it's really only getting 68.6 of the volts. If you hooked it up to a 68.6 volt battery with no internal resistance, it would be, consistent with what it's doing right now. All right, calculate the rate at which the speaker is using energy. So rate is power. So we don't have to think about I because there's only one I. We have to think about what R we want there. So the current is 0.458. And we want to know how much energy is being converted to heat. Well, the 150 ohms is what not to heat, sorry, I'm tired, to sound. This is what's making sound. We don't want the 3 ohms because that's making heat. We want to know how much is making sound. So we only want to use that. So we have a 31.5 watt speaker. All right, now calculate the rate at which the battery is generating heat. So we want I squared times the resistance of the battery. So 0.458 times the 3 ohms, or 0.629 watts. So almost 1 joule per second is heat inside the battery. All right, now we want to find the efficiency of the circuit. There's 2 ways to do this. Well, there's probably more than 2 ways. One is kind of cool, which I didn't do in the lecture. We got 68.6 volts. We wanted 70 volts. So if there's only one thing, if there's only one appliance, you can do, well, this is the voltage I got over this is the voltage I wanted. You can't do that if you have I'll draw a picture in a second. So this is 98% efficient, which is, I think, what we had in the example problem, the lecture notes. That's just a coincidence. You can do that because it will only have one thing hooked up. But if I make a more complicated problem where you have the battery, some internal resistance, and multiple things hooked up, then you can't use that trick. But I'm totally fine if you're like, oh, this makes sense. I wanted 70 and I got 68.6. All right. The other way to do it, which might be more concrete, is we're going to do the useful wattage because we have all the wattages that we calculated over the total. Okay, what did I get? I got 31.5 watts of surround sound. This is my sound bar on my TV or something. I got this amazing, high fidelity sound. But in order to do that, I had to generate both sound and a little bit of heat. And so you get 31.5 over 32.129 or 98%. So pretty freaking efficient. Okay, that was question 1. Question 2, you have a 9-volt battery with some internal resistance, and you hook up a 7-ohm light bulb. A, calculate the current in the circuit. Hopefully that is old hat and you can, I don't know why they say do it in your sleep, but do it. I don't even want you to do it without thinking. Anyway, I hope it comes super easy to you. So about 1 1/4 amps going through this circuit. There's only one loop. And so no matter where you count the electrons, you're going to get 1.22 coulombs per second. Okay, calculate what voltage we really get. We don't really get 9 volts. So the terminal voltage is the idle voltage minus IR. We thought we were going to get 9 volts, but we have to subtract that amount, which is, I don't have it spelled out, hang on. We lost almost a 1/2 volt. So 8.5 volts. Okay, calculate the rate at which the battery is generating heat. So hopefully that formula, I like this, is second nature to you, right? Oh, that's power. Power equals I squared R. 1.22 squared times 0.4. Is that a 0.4? My, yeah, because it's inside the battery. Okay. So 0.595 watts. So it's generating about 0.6 joules every second of heat. And we want to know, hey, how much energy did I lose to heat in 38 minutes? Okay, so the first thing you have to do is convert that to seconds. So 2,280 seconds. And then energy equals power times time. And the power is 0.595 watts. And the time, so again, that's a joule per second. So we multiply by 2,280 seconds. The seconds cancel, and you get 1,357 joules of energy turned into heat. Okay. Question E, let's figure out how bright the light bulb is. So the power is I squared R, and the current is 1.22 squared times R. So you are getting almost 10.5 joules per second of light. And we want to see how efficient that is. So that is the useful energy over the total energy, or useful wattage over total wattage. And we wanted light, so we got 10.42 joules per second of light, but in order to do that, we had to pay or use up 10.42 plus the 0.595 watts So the efficiency is 10.42 over, come on, Miss Scrappy, how come you don't have that written? 11, almost 11 even. And I got 94.6. So again, it's not always 98%. I just make up the numbers. And so 94.6% efficient. About 95% of the energy was useful and 5% was lost as heat. Okay, so I want you, this is a long worksheet, so hopefully gives you really good practice so that, again, these things become second nature. Okay, so what I want you to see is what we have here is same battery, but instead of a 7 ohm bulb, we have a bulb with less resistance. So you might think it is going to be more efficient, but what's going to happen is, since this the resistance has gone down, the current will increase. And so if you've got more electrons going through this resistor per second, it's going to generate more heat. So it's actually going to be less efficient. So that's what I want you to see with this question. So I equals V over R. So 9 volts over 1.4 total. So it's 6.43 amps. Okay, so a lot more current. Now let's calculate the terminal voltage of the battery. So again, it's labeled as a 9-volt battery, but because we have so much current going through it, it's going to lose, you're going to have a lot of electron collisions, and you only have, it's really only a 6.5 volt battery, losing a lot of energy. The more current you have, the more energy you're going to lose going through the battery because the more collisions you're going to have. Okay, let's calculate the rate at which the battery is generating heat. So rate is power. There's only one current. It's a doozy. And the resistance is 0.4. So you are getting 16.53 joules per second of heat being created. And now let's see how much energy is lost to heat. Energy equals power times time. We know the power is 16.53 joules per second. And I'm going to do a shortcut here. I've got 38 minutes, but every minute is 60 seconds. So I'm just going to write it like that. And we have 37,683 joules of heat wasted as heat. All right, hope things are making sense. Now we want to see how bright the bulb is. So let's make it a different color. Okay, so the wattage is I squared R, and the current is 6.43, and the resistance is 1. So that is 41.3 watts of light. And now we're going to find the efficiency of the circuit. Now, if you, I read an article once that said, you know, when office buildings, during the winter, you might count all of this as useful. You might want to say, well, I'm heating the building anyway, so this is 100% efficient because I'm getting a little bit of light and a little bit of heat or a lot of heat, but I want heat. It's just going to save me on my heating bill. So you could say that was 100% efficient. You know, on some level, it depends on what you want. If you don't want heat, then that's going to be wasted energy. But if you do want heat, then it's not. So I only really, in this case, I only really want the light, but in order to get that light, I have to use some energy clearly for the light. Can't get something for nothing. And I have to use some energy to get out of the battery. And so this is a shockingly 71.4 efficient system. So what I don't want you to think is it's the battery itself. You can't say how efficient is this battery. It depends on what you hook up to it. The more current you draw, the less efficient this same battery becomes. That's the point of this problem, is that the efficiency is a function of how much current you have in it, in the system. Okay, the last question, and this is a stretch question to practice your algebra skills. So you have what you think is a 12-volt battery, right? It's labeled as 12 volts. You hook up what you know is a 5-ohm light bulb. And in the lab, you're going to use a measuring device called a voltmeter to, shocker, measure the voltage. And you get that it's actually only a 10.5 volt battery. That's easy to do, right? You can measure the voltage without any current, and then you can measure the voltage in this system. The reason I wrote this question, I guess, is because that is easy to do. Finding the internal resistance of the battery is complicated. Okay, but measuring the voltage, we will see, you just have the thing, and you have the two probes, and you measure the voltage. Okay, so that's what we're doing, is we're measuring what's easy to measure so we can figure out what the internal resistance is. Okay, so then the question is, what is the internal resistance, and then find the current. So there's a couple of different ways to do this. Let's just, again, it's not always obvious. We're looking for the internal resistance. So let's start with, I've got two voltages, so let's start with that equation and see if that works. So the terminal voltage equals my ideal voltage minus IR. And I got 10.5 volts. That's from terminal to terminal. I hoped to have had 12 volts. The problem is this R is not the 5 ohms. It's this R that we don't know. So we're a little stuck here because we don't know I and we don't know R. But the other thing we know, so we're like, okay, well, that didn't maybe help. The other thing we know is that I equals V over R tote. So that's equal to the 12 volts over 5 plus R. Okay, and so again, this feels like not very, I don't want to say rewarding. I can't think of the right word. It feels a little ambiguous maybe because you're like, I still don't know I and I still don't know R. But what we have here is two equations and two unknowns. So we're going to take this relationship and we're going to plug it in for I. That's what I meant by some tricky algebra. And then I'll show you the easier way to do it. So then we have 10.5 volts equals 12 volts minus this whole thing. And this is confusing because that's not a variable. 12 over 5 plus R times R. Okay, and then we're going to subtract 12.5 from both sides. And so we get minus 1.5 equals minus 12R over 5 plus R. And that's good that these are both minus, so then I can multiply both sides by minus 1 and get rid of that. And then we're going to cross multiply, and we get 1.5 divided by 5 plus R equals 12R. And then we're going to distribute the 1.5. And we get 7.5 plus 1.5R equals 12R. We're in the home stretch. Subtract 1.5 from both sides. And you get 7.5 equals 10.5 R, and then divide both sides. Sorry, this is kind of in the middle of other stuff. Divide both sides by 10.5, and you get R equals, and hopefully we're right, 0.714. So that makes sense because internal resistances tend to be small, and you get 0.714 ohms. Okay, so that was tricky because you had two unknowns here and you had two unknowns here, and so you had to algebraically combine the equations. Okay, I'm going to delete some of this stuff and to show you a different way to do it. It's a little bit easier, but mathematically, but a little bit harder conceptually. Okay, the other way to do this that is a little bit, definitely mathematically easier, is to say, you know what, that 5 ohm light bulb doesn't even know the 12 volt battery exists. All it thinks it has is what it gets from terminal to terminal. So it thinks it has a 10.5 volt battery. So, oh my God, that's easy. That's an old school circuit. So the current is going to be 10.5 volts, because that's all this really gets. I've already corrected for the energy loss, over 5 ohms, and you get 2.1 amps. Okay, because that's what this means. This 5 ohm light bulb thinks it only sees a 10.5 volt battery. And once you know the current, then you can do what we weren't able to do before. Terminal voltage equals ideal voltage minus IR. 10.5 equals 12 minus this 2.1 times R. Okay, and then you get the minus 1.5 equals the minus 2.1 R, and you get the R equals the 0.714. Okay, so a little bit easier mathematically, and if you can understand that conceptually, that's awesome. So you see we get the same thing we had before, and then what I didn't do before was to find the current in the system. But we did that up here. I equals 10.5 over 5, 2.1. Bear with me 1 second. The other way to do this is I equals V over R tote. So you can check your work. The real voltage is 12 volts, and the real total resistance is 5 plus the 0.714. Right? There's really a 12 volt energy provider and a light bulb and some internal resistance. So that is 2.1 amps as well. So that's, again, a nice way to check your work, to say, well, I can think of it as a pure battery, a imperfect battery, and two things that it's connected to, which is what you really have. You really have a 12 volt battery and 5 plus 0.714. Or just check the current. Just you can say it's as if I had a perfect battery with smaller voltage, but I only have the light bulb. I didn't have the inside resistance, and you get the same thing. All right. So that was a long worksheet because these are hard questions, and so just enough stuff to give you practice. So hopefully that went well, and thanks for listening.